Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, I'm going to look at one of the application aspect of the concept of an electric charge, and especially we're going to look at an aspect of electric potential in this specific illustration. Now, in this case, we're going to combine that one with the equipotential services, which I'm going to mention basically for the sake of what we refer to as a reference. Now, in this particular case, the concept of equipotential services from this specific previous is going to be the one which we are going to particularly, perhaps I can give this one in terms of an illustration as well, so that we move to our evaluation, which I'm given on the left side of my board. So in this case, if we consider an electric field which can be given in this specific part as such, we're going to see that these are going to be field lines which have been illustrated using the arrow which I've given above. Now, for equipotential services, these are ones in which all the points are at the same potential. Now, I've given an example of this specific, illustration in my previous discussion. And in this case, I'd, mentioned that for these equipotential services, the potential difference between two points of this specific services are going to be 0. Now, if you consider, for instance, the potential at this specific point A and B, so we're going to consider this one as VA and VB. So in this case, the potential difference between two points of these specific services are going to be 0. So we're going to consider perhaps the difference between VB and VA in these specific equipotential services, and the difference between the two are going to be 0 given as such. So in this case, this implies what we refer to as an equipotential services. So we can define an equipotential service as a service in which all the points are at the same potential in that specific summary form. So in this case, no work is done in moving a charge from one point to another in this particular kind of services. And of course, we're going to see that the services must be perpendicular to all the electric fields at a particular point. So in this case, I can give an illustration of this. So for this electric field which is moving from my left to right, then we can illustrate the equipotential, as lines which are going to be given in these specific dotted lines. So these are going to be equipotential lines between two charged plates that are parallel. So in this case, they are going to be perpendicular to these specific lines. So in case we come across them, we're going to identify them. Now, for the sake of perhaps clarity, we're also going to use an illustration for the dipole. So in case we have this specific illustration for the dipole, just give an example of this. So we're going to have this one given as such. So I presume that we had talked about the concept of the direction of the field lines, and of course the aspect of these distances, and of course the concentration and the magnitude. So for this case, I'm going just to give this rough illustration of these equipotential lines, and in this case they are going to be illustrated given as such. Passing through these specific lines, as we have said, they are going to be perpendicular to the direction of these fields. So we're going to see that these equipotential lines which are dotted for the two specific charges are going to be equal but oppositely charged. For the equal and oppositely charged particles, they are going to be equal. Now, in particularly, I can just give that one in an elaborate way, but these are going to be the lines which are going to be parallel to these field lines for a dipole, and then they are going to be distributed as such for these specific particles. Now, later on, we're going to check on their specific concentration, and particularly in another illustration which is going to be more elaborate. But I wanted us to identify what basically we refer to as equipotential lines, and of course equipotential services, which we have said are the ones in which all the points have the same potential. Now, that one having been said and done, we're going to look at this specific evaluation which I've given for the example on my left side of the board, whereby we're going to consider this specific aspect for what we refer to as a picture tube. This is part of the previous models that we have for the television TVs, which of course use the cathode ray tube using as such. So this is going to be a tube which is basically a vacuum where we're going to see that there's going to be motion of an electron due to the heated element from the cathode given as such. So in this case, we're going to consider this specific model, whereby we're going to see that if an electron in this specific tube is going to be, of course, accelerated from rest through the potential difference of 5,000 volts, this is going to be a high voltage kind of, of course, a scenario whereby we're going to have an electron accelerated in this specific tube through a potential of 5,000 volts given as such. We're required to find the change in electric potential of this specific electron. So this is going to be the change in electric potential of this specific electron accelerated in this specific cathode ray tube. And we are also going to be required to find the speed of this specific electron. Now this is going to be a direct application of our previous discussion we had on electric potential. And of course I can just mention the ones which we had done an evaluation. So we had said that the change in potential can be given as a product of the charge and the voltage which is being applied for the this is specific as CRT or cathode ray tube for this electron in terms of volts. So we're going to have this one given in terms of the charge. So this is the charge of an electron which we had given as 10 negative 19 coulombs times. So this is going to be 5,000 volts, and this is going to give us the change in, of course, potential given as delta U. So this is going to be giving us a value of negative 8 times, of course, 10 negative 14 volts given as such. So this one, given the change in potential in terms, we're going to give them in terms of that dimension, but I'm going to do away with this negative sign due to the this change in potential, which is a magnitude, and this was given due to the charge of this specific electron, which I had said is negatively charged. So that's how we're going to find this specific change in potential, and then we're going to be required to find the speed of this specific electron. Now the change in potential energy is the same as the change in kinetic energy, which can be given in terms of from classical mechanics, we have half mv squared given as such, whereby this mass is going to be the mass of an electron, and then we can find this one through a substitution. So we're going to have this one as a half. So the mass of an electron in this specific case is going to be given in terms of this specific quantity. But before that, maybe we can do an evaluation for the speed using this specific formula. So let's consider this one as our equation 1. So we're going to make a velocity subject of the formula by having a v squared equivalent to the change in potential. And then we're going to have this one times 2 for this specific divided by the mass of this specific electron. So for us to find a v, which is going to be, of course, a positive velocity, we're going to do a summary for this so that we can, so implying v is equivalent to the root of 2 change in u over m given as such. So perhaps I'm going to give a figure for this in case we need to do an evaluation. If you find a different answer, kindly give us in the comment section so that we can do a rectification for that, especially for this constant for the mass. Of course, that's going to be having an implication. So in case we come across a different figure from this one, meters per second given us. So this 1.326 times 10 negative 22 meters per second. But of course, we're going to, of course, consider this specific one for the various dimensions. Remember, we had given the unit of this specific proton given as 9.1 times 10 negative 31 kilograms. And kindly confirm from the constants on the mass of electrons so that we can be able to find the correct figure for this. In case we find a different one, assist us in order to do an evaluation and change this specific figure. So I've considered this one from the work energy theorem about the change in kinetic energy, and that is going to assist us doing various evaluation of this specific nature for electric potential, especially evaluations which we may come across in our subsequent discussion. So that is it for now, guys. Bye, God bless you. Catch us in our next video.